Hello everyone. So in the last part of the lecture, we had started discussing the concept of traction, and next what we are going to discuss is how this concept of traction leads to the concept of stress. Now, or rather, more specifically, the state of stress at a point. Now, uh, the moment I say this phrase, state of stress at a point, uh, I believe many of you will start remembering what you studied in your first year mechanics as well as in your fluid mechanics course, and certainly thermofluid science for the manufacturing guys. Uh, and that is fine. Now, the unfortunate thing is, in many of the textbooks for mechanics of solids, this sort of similarity between fluid mechanics and mechanics of solids is not at all highlighted. Now, this is something which I wish to remedy in our course here. So you will see that there is a lot of similarity, at least in the initial parts of how we discuss or how we develop the concept of stress starting from traction. In fact, the derivation that leads to the connection between traction, the mathematical connection between the traction and stress, you'll see it is exactly the same that you have studied in fluid mechanics. I believe that part was already covered. Nevertheless, I still wish to highlight it here in mechanics of solids, not just as a way of recap, but to highlight one very important thing which you may not have realized while studying fluid mechanics. And that is, you see, this relation between traction and stress, it is mentioned in many of the textbooks. Okay, in many of the textbooks of certainly fluid mechanics and many of the textbooks of mechanics of solids or solid mechanics, mechanics of materials. However, especially when coming from the background of mechanics of solids or mechanics of materials, what is sometimes missed by those authors uh, is uh, is that they forget to mention, or somehow they do not highlight it, that this connection between traction and stress holds true even if the body is not in static equilibrium. I repeat, this connection that we will develop, we will discuss it very well, between traction and stress, it is valid whether or not the body is in static equilibrium. So even if the body is in motion, no problem, that relation will hold true. So this is the thing which you may not have realized while studying fluid mechanics, because there this thing, the fluid particles were not in static equilibrium, because even though statics was covered perhaps in the first in the initial chapter of fluid mechanics, of your fluid mechanics course or thermofluid science, but later on you certainly studied fluid dynamics. Okay, the fluid was in motion, and even then the uh, the famous Navier-Stokes equation for Newtonian fluids, that held true, and in the derivation of the Navier-Stokes equation you still had that connection between the traction and the stresses embedded. So this connection is very true even if the thing is not in static equilibrium, and that same concept holds true for solid mechanics also. Now, I think the reason that most authors of these textbooks, they do not, or they forget to mention it, is because most of the problems that we study within the scope of our syllabus, and certainly that will be again the case for our third year course of mechanics of solids here which you are studying, is that almost all the problems will be in static equilibrium case. That does not mean that relation is not true when the body is in motion. So with this background discussion, let us actually try to develop our discussions towards the state of stress at a point. And the plan is as follows. So So when we want to discuss the state of stress at a point, uh, what we'll do is we will uh, we will start our so let me write this down. So we'll start by considering the balance of linear momentum. So this again should highlight to you how close the connection is between mechanics of solids and fluid mechanics. So this is our plan that will start our discussion with the balance of linear momentum. Okay, now when we do that, uh, you will see that we will end up using one another very important balance principle, which is the balance of mass or the conservation of mass, which you studied very well in your fluid mechanics course or your thermofluid science course. But again, here I want to emphasize it that many of our textbooks of solid mechanics or mechanics of solids are written in such a way that it kind of gives the impression that by not referring ever to the balance of mass or conservation of mass, it kind of gives the impression that those kinds of balances are, or that kind of balance for mass is perhaps important only for fluid mechanics, as if the continuity equation holds only true for fluid mechanics and has nothing whatsoever to do with solid mechanics. That is completely wrong. As long as you are working under the purview of continuum mechanics, in general continuum mechanics, it doesn't matter whether it is fluid mechanics or solid mechanics, balance of mass has to hold true. Okay, you have no other option. That must hold true. That is the foundation. Now we'll use that balance of mass in our balance of linear momentum, and you will see how the balance of linear momentum will help us very naturally to go towards this connection between traction, which we studied in our previous part of the lecture, and the state of stress which you want to develop towards. Okay, so the things, the kind of things that we are going to write down here, it will be very reminiscent of the things that you studied in your fluid mechanics or thermofluid science course. So for balance of linear momentum, we will write this first of all in the integral form. Okay, now if you remember, and because this is kind of a repetition for all of you, both the mechanical and the manufacturing guys, I will not go into the deep details of discussing this. However, if you really want to have a more elaborate discussion, maybe for the purpose of revision or maybe to clear some lingering doubts, maybe you can post this in our discussion forum or something similar, maybe some email or something, and maybe I can record a separate lecture altogether as a complement to this. Okay, so so the plan is like this, that I will discuss the balance of linear momentum, writing out everything completely, but not discussing in too much detail. So the first thing that we are going to write is the material derivative, okay, the material time derivative of the linear momentum written in integral form. So rho is the mass density of the material, v is the velocity, of course, and that is integrated over a certain volume. Let's consider a three-dimensional volume to keep things general. Okay, so you understand that this balance of linear momentum is just a rewrite of the Newton's second law of motion. Okay, so that's basically what it is. It's basically a sophisticated way of writing F is equal to ma. So what we have written here, F is equal to ma, or perhaps even more generally, F is equal to the time rate of change of the linear momentum. That's that form of the Newton's second law. So that is this on the left hand side, that is the time rate of the change of linear momentum, this rho v. So you can think of this like rho times the dv, the density times the dv, elemental volume, that gives you the elemental mass, and elemental mass times the velocity, that gives you the linear momentum, and integrated over the volume, that gives you the total linear momentum. Okay, and ddt of course is the time derivative. Okay, and on the right hand side we need to write down the various contributions from the forces. Now these forces can be body forces, they can be surface forces. So for body forces, we'll write down like this. So rho is again the mass density. So B is the force per unit mass, and we integrate over the entire volume. And finally, and this is where the first step towards establishing the connection between stresses and tractions will take place. We are going to write down the surface forces in terms of the traction. Okay, so this is T ds. Okay, where the ds is the elemental surface and s is the entire surface of the body under consideration. So you can imagine that we are again, of course, considering a general three-dimensional body like we had been considering in our previous part of the lecture. So a general three-dimensional body like this, and now what we are doing is that in the previous class we had considered this traction vector to be concerned or relevant to this internal point. What we are doing today is to consider this to be a point, this for a point lying on the surface. So instead of lying this point P lying inside it, we are just shifting this point P on the surface. There's absolutely no difference. Okay. Okay. Now you see, first of all, what we'll do is we'll deal with this left hand side. Okay, we'll deal with this left hand side, and we want to recast into a form such that this integration which is having a ddt in front of it will be recast in a way such that there is nothing sitting in front of it. So it will start looking, this integration, this volume integration, it will start looking like this. Okay, you see there is nothing in front of this integration, there is no ddt term here. Furthermore, our plan later on will be to somehow recast this also in terms of a volume integral, but that is for later. Let's not worry about that right now. So first of all, we'll deal with this left hand side term. Now ddt rho v dv. Okay, now this is the part where I will quicken my pace a little bit. Had this been a face-to-face lecture, I would have spent a little bit of time asking some of you about how we proceed from here. So maybe you can pause your video a little bit and think how we can proceed. So basically what we are going to do here is to use the Reynolds transport theorem. Okay, so some of you may be wondering, like, Reynolds transport theorem we studied in fluid mechanics or thermofluid science, what is it doing in solid mechanics? Well, as I said, there is a very close relation as far as the development of these fundamental concepts is involved, and practically there is no difference between the way we deal with fluid mechanics or solid mechanics. It is all part of continuum mechanics. Okay, so we are going to use the Reynolds transport theorem, and what we'll do is we'll write it like this: the del t of rho v dv plus the rho v term again. Okay, this rho v is the same rho v as here, but now this surface term. Okay, now we don't want to keep it in the form of a surface term. So you understand that this is basically so we are writing from here to here using the Reynolds transport theorem. Okay. Now I don't want to keep it in the form of a surface integration. I want to recast this in a volume integral form. So what can I do? I can just use my Gauss divergence theorem, and very encouragingly, every time I have asked this question to your seniors in the past 2-3 years, inevitably someone or the other gave the correct answer that we have to use the Gauss divergence theorem. So that's very nice, and I believe many of you have already answered this in your head correctly, that this is indeed the Gauss divergence theorem. Anyway, so So what we'll do is we'll rewrite this entire thing in terms of a volume integral like this. This remains as it is, but this one will be in the form of a divergence. Okay, this will be in the form of a divergence. The rho v term will remain as it is. Okay, however, we have this entire thing is under this volume integration. Okay, so because when you convert this to the volume integration, you have the integration over volume of over this. Now you see, what is this thing? What is going on here? I have not put a dot, I have not put anything here, so it is a little bit confusing, because this rho is a scalar, no problem, but this v is a vector. This is again the same vector v. So if we had put a dot here, what would have happened? If you had put a dot here, then this entire entity would have become a scalar quantity. Now the divergence, so this gradient operator with the dot, that is the divergence, that cannot act on a scalar. So surely we cannot have a dot between this rho v and this v. That would have made it a scalar. Now that this divergence would be just wrong. So this is not a dot. What should it be? Well, the correct symbol that we are missing here is the tensor product or the dyadic product here. Okay, so this is the part where I am not going to discuss too much, because I believe this should have been covered in your fluid mechanics courses. But again, I am telling you, if some of you have some problem, please let me know through the discussion forum or through email or something, and maybe I can go into the into some more detail of it. Okay, now what we'll do is we'll take this expression. Okay, we'll take this expression and we'll try to see how this can be simplified a little bit, because you see, I have started with the balance of linear momentum, and in that process I had told you that even when you are considering balance of linear momentum, somehow the balance of mass has to be used. I told you that, but till now we have not used it. You will see how that comes into play. Okay, so in the next slide or in the next page, I'm going to just repeat this thing and then continue. Okay, so I'll just quickly repeat it. So d dt rho v dv. This one, I'll just repeat this last line here quickly. So integration over volume, del t of rho v plus divergence of rho v again. Okay, now comes a very crucial step. What I will do is I can break this up using the simple chain rule of derivations. So this will be rho del v del t plus del rho del t with a v. No problem there. But this one is far more complicated. Okay, and again, because I believe this would have been covered in your fluid mechanics or thermofluid science, I will not cover it in detail. Okay, but again, the promise remains that if you're not sure about this, do let me know. So proceeding, what we'll do is we'll just use one vector identity or a tensor identity, so to speak. We'll quickly write down the expression. So when you break this thing apart, okay, carry out the divergence properly, so you get this. So it's as if this one is first acting on this, but it's not so simple as that. Okay, so you get this thing, and then by some magic you get this thing out, and this one operates on this, you get this. Please note here that this is just rho v dotted with the grad, and this entire thing operating on the v. Please note that. Okay, so it is not this part is not the divergence of v, it is just the grad of v. If you just consider it separately, that is the grad of v. I think it is much more intuitive if you think of it like the rho v dotted with the gradient operator. So that is like a scalar operator that is operating on this v. Okay, I won't spend too much time on this anymore. So what happens now is that we can collect some common terms. And you see what we'll do is, you see there's a v here, v vector here, there's a v vector here. We'll take that common. So v vector common, del rho del t plus delta dot rho v. Keep that together. Next, whatever remains, this rho del v del t plus rho whatever this term is, that will take together, taking the rho s common. So del v del t plus v dot grad v. Now you tell me, whatever I am doing here, is it not the same as what you have encountered in your fluid mechanics or your thermofluid science course? I believe you will definitely remember it to be almost the same thing. In fact, not almost, exactly the same thing. Now you tell me, what is this part? Okay, I want you to focus your attention on this part. Del rho del t plus delta dot rho v. What is this? Okay, so by conservation of mass, what we have actually is del rho del t plus delta dot rho v. That is equal to 0. In the context of fluid mechanics or thermofluid science, I am sure you have come across this equation, and this is the famous continuity equation, and this again comes up in the context of studying solid mechanics. Okay, in fact it is like a very artificial distinction as far as these initial parts of our lectures are concerned. It's exactly the same thing, it's just continuum mechanics right now. Okay, so because this thing is 0 in general, because you have conservation of mass, so this entire term is 0, which means basically what you have is that d dt integration rho v dv is equal to integration over the entire volume of this term. So basically I'm just rewriting this term here. And what is this particular form? So this is nothing but the material derivative of the velocity vector. So this is rho dv dt. Okay. Please note that you should not fall into the trap of very naively taking this d dt inside this volume integral. Please do not do that. You have to use the like in the previous slide you can see, please resist the temptation of just arbitrarily taking this d dt inside it, okay, and using the chain rule. So you have to properly use the Reynolds transport theorem and then proceed. Okay, so when we do all of this, we end up with this thing, and this is how and this is what I meant when I initially said that we have to consider the balance of linear momentum, and you will see that the balance of mass will be inherently used here. Okay, and as you see, we have actually used this, the conservation of mass or the balance of mass we have actually used. So we end up with this particular expression. So if we go back to our original equation of the balance of mass, this left hand side we have kind of simplified, and we have achieved our objective of making this integration to be rewritten in such a form that there is no time derivative sitting in front, as you can see here. So this d dt of this is a volume integral. So this has been rewritten in a form such that there is no time derivative, there is no material time derivative sitting in the front. Okay, now if we substitute this expression back here, you will see that on the left hand side the volume integration is again like this particular volume integration form. Okay, so since this very important step is done, I'll let you take a breather and stop this part of the lecture here and proceed exactly from this point in the next part of the lecture. Thank you very much.